Or I should say, when would that be a concern? You can always rescue it by taking a delta t that is small enough, right? It's usually not a concern for scalar ODEs, but for system of ODEs. And especially when you have a PD, that's what we are going to be talking about starting next week. If you have a partial differential equation, the standard way to solve it is to discretize it spatially to get a system of ODEs, and then solve the system of ODEs. And when you have a partial differential equation, you have a billion grid points. You discretize it, you get a system of a billion ODEs coupled. All right. And the lambdas you have, right? The lambdas you have to use to analyze the stability, the long-term stability, is actually the collection of eigenvalues of that billion by billion matrix. Some of them can be very, very negative. Okay, I mean, you can use a time integration scheme like that, but the problem is that you have to choose an extremely small delta t, not because you have to use that delta t to make the solution accurate, but because if you don't use such small delta t, your solution is going to blow up because of the very negative eigenvalues. So that's actually a property of the system, right? And it's a property of the system we call stiffness. So stiffness is when we have a system of equations, when we have du dt not equal to lambda times u, but a matrix A times u, and our u is a vector u1, u2, etc. up to u, let's say m. Okay, we have a system of m equations. They are coupled with a matrix or even some nonlinear systems. What happens for a stiff system is that when you look at the eigenvalues of A, has many different orders of magnitude. Okay, has orders of magnitude difference. One of the examples I like to illustrate is that think of the heat transfer example we looked at in our first lecture, right? We have a cube and we have a heat that blows onto the cube. Okay. Now think of, instead of making the simplification that the cube has uniform temperature, you are actually solving for the heat transfer inside the cube. What happens is that the heat transfer inside the cube is going to be fast, right? It's going to be fast. The coefficient is going to be fast. So what you end up with, so let's say you are considering two different points. You are considering two different temperatures on the upper and lower part of the cube. And you're solving the equation d temperature 1 dt and the d temperature 2 dt is equal to something times T1 and something times T2, right? Okay. What is the result of these coefficients? The result is you're gonna have two parts, right? One part is due to the heat from the air. That coefficient is gonna be normal. It's gonna be whatever we derived on the first lecture. But you are gonna have another component that is due to the heat transfer between these two parts, and that is going to be very large, right? So you're going to have something like 1,000, for example, times negative T1 plus T2, and here you're going to have 1,000 times T1 minus T2, right? That's just due to the heat transfer between these two parts. And then you have something extra. You have the heat transfer from the air. So let's say plus T air minus T1, right? So that's heat transfer from the air. And then plus T air minus T2. That's from the heat transfer from the air. So effectively, you have two components. One component that acts very fast, acts very strongly. The other component acts very weakly. And if you discretize the equation dt over dt, what do you get is that the coefficient on T1 is going to be minus 1001. On T2 is going to be plus 1000. On the second component, on the second equation, the first component is going to be 1000. On the second component is going to be a minus 1001, right? If you analyze the eigenvalue of this matrix, what do you think you're going to get? Well, it may not be obvious to you that you're going to get two eigenvalues that is 1000 times different, but if you look at enough physical systems, discretizing equations, it becomes pretty obvious. So if you take eigenvalues, is it minus 1001, 1000, and 1000, right? And well, I think I missed a zero here. And minus 1001, it's going to become like minus 2000 and minus 1. Basically, you have two eigenvalues, very different. In order for you to solve the equation accurately, you probably only need to using a delta t that is much smaller than 1 over the minus 1 eigenvalue. But in order for your system to be stable, your delta t has to be less than 1 over the minus 2000 eigenvalue. So it's a huge discrepancy between the amount of delta t, the amount of computational resources you need to spend on ensuring accuracy versus the amount of computational resources you need to ensure stability. Right? So basically, to summarize, we are discussing the problem posed by the stability region having a finite extent in the negative region. The problem is when you have very different eigenvalues, one eigenvalue may be over here, another eigenvalue very far away in the negative region, then you need to have a tiny delta t to be stable. Right? So that's a problem observed pretty early. And a lot of people have thought about ways to solve this. And right now, we have a commonly accepted way to solve this, although it's not perfect. The way is what we call using an implicit method. So the way to deal with stiffness is what we call implicit method. So what do I mean by implicit method? I'm going to introduce by just telling you an example. And the example, first of all, we want to compare against the explicit method. That's actually the method. All the method we have studied so far are explicit method. I'm going to compare against the forward Euler. The forward Euler is UK plus 1 minus UK divided by delta t equal to f of UK, right? The implicit method, a prominent example is what we call a backward Euler. Instead of a forward Euler, it's backward Euler. This is backward Euler. It looks actually pretty symmetric to forward Euler, right? Instead of using u of k plus 1 minus uk, we use u of k and uk minus 1. But actually, there is a problem. There is a reason why we actually prefer explicit Euler. I mean, prefer a forward Euler most of the time. Is because whenever we have a complex f, right, applying an implicit method is actually pretty painful. So let's say f is equal to exponential, f of u is exponential of minus u plus sine of log u. That's kind of one of the functions some of you gave to me like early in the lecture. So let's say f of u is like this. How do you actually use the implicit method? You have to solve a pretty complex nonlinear equation, right? Every single time step, because this is unknown, right? This is unknown. I mean, you only know uk minus 1. In order for you to go from k minus 1 to k, you have to solve an equation. And then from k to k plus 1, you have to solve the same equation once again. And every time step, instead of just computing the next time step, you have to solve a complex equation for every time step. And there is usually no analytical solutions if f is complex enough for you to use a numerical method, right? I mean, if f is simple, you probably have analytical solutions. If you don't, then f is probably not so easy. You have to solve this using some Newton's iteration, for example, right? So implicit methods like this actually has its disadvantage, but the advantage is actually pretty clear. The advantage is that its stability region extends to minus infinity. So let's actually demonstrate that. So if you have uk minus 1 divided by delta t equal to lambda times uk, right? Instead of uk minus 1, which is explicit Euler, we have forward Euler, we have backward Euler. The right hand side is actually corresponds to the first member. So if you have this, then if you collect the unknowns, which is 1 plus, no, not plus, which is 1 minus lambda delta t times uk is equal to uk minus 1. And you have my uk is equal to 1 over 1 minus lambda delta t times uk minus 1, right? The amplification factor actually is 1 divided by something. And now if you take our Euler code, and instead of saying absolute value of this, I have 1 divided by 1 minus lambda. You're going to see a dramatic difference. If I run this, this is what we get. Wait. Yes, I think that's correct. So, well, I think this color range is going to mess me up. So let me actually take a minimum of, let's say 2. Basically, let's actually cap it between 1 and 2. So what you see is that everything is stable except for this region, right? So just to remind you, forward Euler is stable only in a circle around here. Backward Euler is stable for everything except for a circle over here on the positive side of the complex plane. So it completely solves the problem of having huge negative eigenvalues. Okay, so next lecture we are going to look a little bit more on the implicit schemes and introduce you a few good choices of implicit schemes before we move into partial differential equations. All right, see you next time.